Hi everyone, I'm Kevin, and I was working in Jay McClellan's lab with Cynthia Henderson, an awesome PhD student, to create a computational model of visual search based off of a model Cynthia had worked on previously. So here's a rough outline of the presentation. I'll start with some of the background on the work and the motivating questions for our research. After that, I'll describe what we ended up doing, then briefly mention what we're doing now. So let's start with visual search. Visual search is fancy psychology jargon for looking for something. If your childhood was like mine, you should be familiar with Where's Waldo, where the goal is to find Waldo in a big scene. If your current life is like mine, you should be familiar with looking everywhere in your room every morning trying to find your keys. Because psychologists are very imaginative, they came up with equally creative scenes that look roughly like this. So here's one question. How do we do visual search? Many models have proposed interesting mechanisms for visual search, but most are handcrafted and are designed at a high level, only posited to connect to known neurological properties. So here's an even better question that we're addressing. What are the mechanisms and strategies of visual search, and how do we learn and develop these from our basic capabilities? We also want to consider one other question based off of the original intent of Cynthia's model. In visual search, people often make mistakes. A strange but reliable class of mistakes is the false alarm, when we think we see something when it's not there. A related phenomenon is illusory conjunction, when we see two objects and incorrectly combine features to form an imaginary object. It's as though you saw red grapes in a Tyrannosaurus Rex and thought you saw Barney the dinosaur. Yes, I am being kind of ridiculous here, but that's basically the idea. Most models of visual search only haphazardly deal with errors, so here's another question. Why do we make these mistakes, and do illusory conjunctions have anything to do with it? So given these questions, we're addressing them here with Cynthia's original model that we'll be extending. You have inputs here, and outputs here and here. The outputs on the left mainly correspond to locations of objects, and the outputs on the right mainly correspond to object identity. So far, we've managed to modify the network in three major ways. First, we've expanded it from recognizing only two objects to recognizing four objects. One might argue that 4 isn't necessarily better than 2, maybe like in this case. But in our case, 4 does get us in the range of visual search. Although you might think that this just requires doubling the size of everything in the model, the interactions are stranger than that because the model relies on similarities between objects at different locations, yet at the same time requires distinct representations to keep two objects separate. Also good news is that when the model doesn't see objects correctly, it often thinks that there's an object present that has features borrowed from two objects. There's our illusory conjunction. Second, we've trained the model to attend to objects by its identity. It's cued here, and if it represents it, it'll find it here and over here as well, and you won't see any output, I guess, if it doesn't. It's sort of searching, but you might say it's more filtering. Third, it can scan across different objects. If you've done any programming, you know that this isn't hard to design procedurally. What I think is cool about this is that it learned how to do this using only gradient descent on a training set, and has no cues for locations. I actually didn't even think that this was possible before I trained the model, so it was a pretty big win for us. So serial search is kind of cool, but does it really bias anything? Well, we found out yes. I mentioned earlier that we expand the network to recognize 4 objects, and it does. Given multiple objects, it can get the locations and often gets all of the object identities when it's trained to do just that. When the model is trained to do this serial search task, however, and is asked to represent all of the objects in the end, it actually performs better than when it was trained to do this without searching. Weird, right? When asked to do something much harder, it does better on a different task. It's actually so weird that Cynthia insisted on this particular set of statistics appearing because it's actually kind of awesome. My guess is that the model is encouraged to learn to represent all these objects distinctly, and that means that it doesn't get confused at the very end. Beyond being good news for our model, it also suggests that attentional models for computer vision might help with doing image segmentation and object recognition. So where are we now? Well, on the model front, we're currently trying to train the network to take this object detection and this serial searching and do all of it together by searching for a target object. This sort of goal-directed search instead of blind serial search really is the visual search we're trying to work towards, and we can start playing around with things from there. We're also developing an experiment to run through subjects through, so we have our own data on visual search, particularly focused on certain mistakes that people make. So that's the end of my presentation. If you listen to all this and it seems clear, this is a practice presentation for one I have to give actually relatively soon. So hopefully you enjoyed.